Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Hope you and your family will be in good health. Lecture for grade 10, subject chemistry, chapter number 9, lecture number 2, and here is Mrs. Saira Jamal. Dear students, last time we discussed the topic of dynamic equilibrium. Here we have one more example of dynamic equilibrium, and that is dynamic equilibrium in soda. Soda, you know, the fizzy drinks like Pepsi, Coke, 7 Up, Mirinda are the fizzy drinks. One of the example is Coke. They are made such by dissolving carbon dioxide gas in solution of carbon dioxide. In solution to carbon dioxide, and AQ means aqueous solution. Aqueous means water. As we are making solution in water, so it is called aqueous solution. When carbon dioxide is dissolved in solution, we call it aqueous solution of carbon dioxide. It means carbon dioxide from gaseous state is converted into the aqueous solution form. So G is for gaseous state and AQ is for the solution of carbon dioxide. So in order for the soda to remain fizzy, it must be kept under pressure, and kept under pressure is by filling carbon dioxide gas in the solution of carbon dioxide, and then by placing a cap tightly on the bottle will increase the pressure, and it means that the carbon dioxide gas is filled in this bottle under pressure. Under pressure, what happened? Carbon dioxide from the gaseous state is converted into carbon dioxide in the aqueous solution form. It means that carbon dioxide will get dissolved in solution, and that carbon dioxide is then called aqueous carbon dioxide. But once the pressure is released, how can the pressure be released? By opening the cap of the bottle. When we will open the cap of the bottle, what will happen? The carbon dioxide which was in the dissolved form, it will be converted back into the gaseous state. That carbon dioxide will evolve out or come out from the bottle. You can see along with the solution, carbon dioxide will comes out. So it means that what will happen when the pressure is released, the equilibrium will shift back toward the gaseous carbon dioxide due to change in pressure. So by changing any condition, one of the condition in this case is pressure, what happened? The equilibrium is shift in the reverse direction from the aqueous carbon dioxide or from the dissolved carbon dioxide, the reaction is shifted in the reverse direction, which is carbon dioxide in the gaseous state. Carbon dioxide in the gaseous state, when dissolved in solution, that solution of water, AQ I told you is for the water, aqueous, aqueous or aqua comes from water. So forward reaction is carbon dioxide gas when dissolved in aqueous solution, it will be converted into aqueous carbon dioxide or dissolved carbon dioxide. But when we open the lid or open the cap of the bottle, what will happen? We are decreasing the pressure. So when the pressure will be decreases, what will happen? The reaction will favor in the reverse direction, or the reaction will move in the reverse direction, and carbon dioxide from the dissolved form will be converted back into the gaseous form. So this is one of the example of dynamic equilibrium. Equilibrium state, I told you in my previous lecture, is that the state of a reaction in which the rate of forward reaction become equal to the rate of the reverse reaction. And why it is called dynamic equilibrium? It is called dynamic equilibrium because with the naked eye or macroscopically, it seems that the reaction has stopped. But actually what happened, the reaction continue at molecular level, or in other words, you can say that the reaction will continue at the microscopic level. So molecular level or microscopic level, the reaction continue. We cannot see it with the naked eye, but it actually continue. So that's why this type of equilibrium in which the reaction never goes to completion is called the dynamic equilibrium. Next topic is example 9.1, writing the forward and the reverse reaction. This is a reversible reaction, that is nitric oxide, 2 moles of nitric oxide after oxidation. Reaction with oxygen or addition of oxygen is called oxidation. So oxidation of nitric oxide or reaction of 2 moles of nitric oxide with 1 mole of oxygen gas will produce 2 moles of nitrogen dioxide. This is a reversible reaction, and this double arrow actually indicates the reversible reaction. The double arrows indicate that this reaction is a reversible reaction which can favor in both direction or which can move in both direction. It can move from left to right as well as it can move from right to left. And when the state will reach when the rate of forward reaction will be equal to the rate of reverse reaction, and that state is then called equilibrium state. Now in this example they ask about write the forward reaction and the reverse reaction for this reversible reaction. Now how to solve this problem? There are two steps. The reaction from left to right is the forward reaction. The reaction from left to right is the forward reaction, and the reaction from right to left, from right to left is the reverse reaction. From left to right, forward reaction, and from right to left is the reverse reaction. So we will write forward reaction and reverse reaction for this reversible reaction. Solution is forward reaction. So nitric oxide and oxygen are the reactants in the forward reaction, and they will react together to form 2 moles of nitrogen dioxide, which is product in the forward direction or in the forward reaction. Nitric oxide and oxygen are the reactants. They will react together and will form the product, which is 2 moles of nitrogen dioxide. Now let us write the reverse reaction. In reverse reaction, if you remember, I told you that for reverse reaction, the product of the reversible reaction will be reactant and the reactants will be the product. Product will be the reactant. So let us see, this is the product, 2NO2 or 2 moles of nitrogen dioxide. 2 moles of nitrogen dioxide will be the reactant for the reverse reaction, and these two molecules of nitrogen dioxide will react together and will give back the reactants, which were the reactants in the forward direction, and those were 2 moles of nitric oxide and oxygen. Oxygen gas will be formed. So for the forward reaction, reactants are react together to give product, but for the reverse reaction, the product will react together and will give back us the reactants. So you can see these are the reactants and these two are the products in the reverse reaction. Now we have self-assessment exercise 9.1. The self-assessment 9.1 is write both forward and reverse reactions and describe macroscopic characteristics of each. Same like the example, but in this case they ask one more thing, that is describe the macroscopic characteristics. What are macroscopic characteristics? Macroscopic characteristics means the properties that are visible to eye, like which we can see with the naked eye, are called the macroscopic characteristics. First reaction is, or the first reversible reaction is, nitrogen, 1 mole of nitrogen react with 3 moles of hydrogen gas and will form 2 moles of ammonia. This is a reaction, a reversible reaction, and for this reaction we have to write the forward as well as the reverse reaction. Let us write the forward reaction for this reversible reaction. Forward reaction is, nitrogen gas when react with 3 moles of hydrogen gas will produce 2 moles of ammonia. This is the forward reaction. Nitrogen and hydrogen gases are the reactants and ammonia is the product. Now let us write macroscopic characteristic. Well, let us discuss the macroscopic characteristics for this reaction. Nitrogen and hydrogen gases are the reactants in forward direction. They react together to give ammonia as a product. Reactants react together will form product. So ammonia is the product in the forward direction, and the nitrogen and hydrogens are the reactants in the forward direction or in the forward reaction. So the reaction in this case, or in the forward reaction case, the reaction moves from left to right, from left to right. Now, reverse reaction for the same reversible reaction is, the product in the first case or in the forward reaction case will be the reactant in the reverse reaction, and the reactant will be the product. So you can see 2 moles of ammonia molecules, they will react together and will give back the reactants, nitrogen gas and 3 moles of hydrogen gases. Macroscopic characteristic for this reaction or for the reversible reaction, ammonia gas is the reactant in reverse direction, react with other ammonia molecule because there are 2 ammonia molecules. So definitely it will react with other ammonia molecule to give back nitrogen and hydrogen gases as a product. And the reaction will move from right to left. From right to left, if you will see this reversible reaction, the forward reaction moves from left to right, and the reverse reaction moves from right to left. This left to right and right to left, for this you have to consider the reversible reaction. Okay, not this reaction. Consider this reaction, which is the main reaction, which have double arrows. This double arrows actually shows that the reaction is reversible. So for when you have to write the forward reaction, we will say that the forward reaction will favor from left to right, and the reverse reaction will favor from right to left. Okay, from right to left. Then we will write this right to left in this form with a single arrow. You can see single arrow for forward reaction and single arrow for the reverse reaction, and when we combine these two forward and reverse reaction, then we will get this net reversible reaction. Got it? Second part of this self-assessment exercise is, hydrogen gas when react with iodine gas, it will form 2 moles of hydrogen iodide gas. So again, the double arrows mean that the reaction is reversible. And for this reversible reaction, we have to write the forward reaction and reverse reaction. So the forward reaction is same. Hydrogen gas react with iodine gas and will form 2 moles of hydrogen iodide gas. Macroscopic characteristic for this reaction is hydrogen and iodine gases are the reactants in forward direction. They will react together because they are reactants. The reactants will react together to give hydrogen iodide as a product. 2 moles of hydrogen iodide will be the product. And the reaction move from left to right. I told you forward reaction always favor from left to right or always move from left to right. Reverse reaction for this reversible reaction is, I told you the product will be reactant and the reactant will be the product because the reaction favors in the reverse direction or it favors from right to left. So from when the reaction will favor from right to left, then the product will be the reactant and the reactant will be the product in that case. So you can see 2 moles of hydrogen iodide will react together to give back the reactants, hydrogen gas and the iodine gas. Macroscopic characteristics for this reaction or for the reverse reaction is hydrogen iodide gas is the reactant in reverse direction, react with other hydrogen iodide molecule to give back iodine and hydrogen gases as a product. The reaction move from right to left. The reverse reaction is the reaction will move from right to left. Forward reaction from left to right and reverse reaction from right to left. Next topic, the very important topic of this chapter, that is law of mass action. Law of mass action is two chemists, C. M. Goldberg and P. Watt in 1864 proposed a general description of the equilibrium condition or state. Like what are the conditions of equilibrium or what are the requirements of equilibrium state, like the reaction will remain in equilibrium state if the following conditions are fulfilled. So these two chemists, they propose a law which is called law of mass action. Statement of this law of mass action is, it states that the rate at which a substance react, substances are A is a substance, B is a substance, A reacts with B and will give C and D. A and B are the reactants and C and D are the products, and double arrows show or double arrow indicates the reversible reaction. So law of mass action states that the rate at which a substance reacts means the rate at which A react or the rate at which B react. It is proportional to its active mass. What is active mass? Active mass is the concentration of A or B or C or D or any substance in a unit called moles per decimeter cube, which is also uh, equal to molarity, or it is also called molar concentration. We have learned it in grade 9 that the molar concentration is the concentration unit, that is molarity, and it is equal to moles per decimeter cube because molarity is defined as the number of moles of solute dissolved per decimeter cube of solution. So active mass means only active mass is the concentration of substance in moles per decimeter cube, and we represent it by bracket or by parenthesis. So the rate at which a substance reacts is proportional to its active mass or its concentration in moles per decimeter cube. And the rate of chemical reaction, what is the rate of this complete reaction? The rate of this complete reaction is proportional to the product of the active masses of the reacting substances. The rate at which a substance reacts, we will consider only A or we will consider only B. But if we consider the whole reaction or the complete reaction, in that case, we have to consider both reactants. And the product of reacting substances product means that A multiply B. Because when we multiply two terms, they will give us the product. So we can also write in this form what is active mass, and active mass is considered as the concentration of reactants and products in units. Which units? In units of mole per decimeter cube. I told you this is also called molarity or also called molar concentration, expressed as square brackets. So instead of writing mole per decimeter cube, we just put these parentheses, and these parentheses means that the concentration is in mole per decimeter cube. According to the law of mass action, the statement is reactivity of a substance is directly related or directly proportional to active mass of that substance. Suppose, let us take the example of a substance A. So reactivity of A is proportional to the active mass of A. Active mass of A, I told you, represented by parenthesis. This parenthesis means that the concentration of A in which unit? In moles per decimeter cube. So it means that greater the concentration of A, greater will be the reactivity of A. Lesser the concentration of A, lesser will be the reactivity of A. So the reactivity of A or the rate of reaction of A depends upon its concentration. And greater concentration, greater will be its reactivity. Lesser concentration, then lesser will be the reactivity of A. So the first part of the statement of law of mass action, that the reactivity of a substance is proportional to its active mass. Second part of the statement is that the rate of reaction is proportional to the product of active masses of reacting substances. Like rate of reaction is proportional to the reacting substances are A and B. Product, I told you, no sign name, there is multiplication sign. So product of A, concentration of A or molar concentration of A into molar concentration of B, this is called product of the reacting substances. It means that the concentration of A and B, if it is greater, so it is understood that their product will also be greater. Lesser concentration means lesser product. So if the concentration of A and B will be greater, then the rate of reaction will also be greater. Lesser concentration, so lesser will be the rate of reaction. It means if we have more reactants, so then the reaction will favor with a greater speed, and then it will give us more product. So these are the two parts of the law of mass action. The first part is reactivity of a substance is proportional to active mass of that substance, and reactivity or the rate of reaction is proportional to the product of active masses of the reacting substances. Derivation of the expression for equilibrium constant for general reaction. Now we will derive an expression or an expression or equation for equilibrium constant, and for any general reaction. For any general reaction mean you will just consider a hypothetical or an imaginary reaction. We are not taking an example this time. So let us apply the law of mass action for a general or hypothetical. hypothetical imaginary reaction. Let us take the example of A animal, A capital A any reactant when react with B moles of any product, B will of any reactant B will give us C moles of capital C and D moles of capital D. So you can see A, small b, small c, small d, they are the number of moles, and capital A, capital B, capital C, capital D are the reactants and product. Capital A and capital B are the reactants, and capital C and capital D are the products. Small a, small b, small c, small d are their number of moles. It means how many moles are appeared in a reaction. This is any general reaction because we are not taking nitrogen gas or hydrogen gas or give ammonia. We just say that suppose we have any reactant A will react with another reactant B and will form product C and product D. This is called general reaction or imaginary reaction or hypothetical reaction. So when reaction will move from left to right, it is called forward reaction. And when reaction will move from right to left, it is called reverse reaction. So according to the law of mass action, as I told you that A, small a is moles of reactant A and small b is moles of reactant B, which will react together and will give C moles of product C and D moles of product D at equilibrium. At the equilibrium state, I know about it. This reaction consists of two reactions, forward and reverse reaction, because double arrows I told you means the reversible reaction, and reversible reaction means that this reaction is actually a combination of two reactions, forward reaction and reverse reaction. So according to law of mass action, we will use the general reaction, rate of forward reaction. According to law of mass action, the rate of reaction is proportional to the product of the reacting substances. So we have the reacting substances A and B. A and B are the reactants, and the rate of forward reaction will depend on the concentration or the product of concentration of these two reacting substances. And the small a and small b are their numbers of moles which appears in the balanced chemical equation. So rate of forward reaction is proportional to the product of the active masses of the reacting substances. And to remove the proportionality sign, we will use a constant Kf. What is Kf? Kf is called the reactivity constant of the forward reaction or reactivity constant for the forward reaction. Just instead of this proportionality sign, we will use equality Kf. That is the constant of the forward reaction. Then rate of the reverse reaction again is proportional to the product of active masses of the product. Product I told you in the reverse reaction will be the reactant. That's why we use the for the reverse reaction C and D will be the reactant. So C a small c and small d are their number of moles. We will do the same for reverse reaction. To remove the proportionality sign, we will use constant, the activity constant of the reverse reaction, that is Kr, and that is rate of reverse reaction is equal to Kr and the product of the concentration of the product, where Kf and Kr are rate constants for forward and reverse reaction respectively. They are called rate constants. At equilibrium state, what happened at equilibrium state? The rate of forward reaction become equal to the rate of reverse reaction. Rate of forward reaction becomes equal to rate of reverse reaction. Now we will put the values. Rate of forward reaction values are Kf A power A B power B, and rate of reverse reaction are Kr C power C and D power D. By putting the values, you can see we will get this form. By rearranging these values, we will get by taking the constants on one side and variables on the other side of the equation. The above equation becomes Kf, which is the rate constant for the forward reaction and rate constant for the reverse reaction. The product concentration of the product we always write in numerator, and the concentration of the product of the concentration of the reactant we always write in the denominator. Instead of writing these two constants, we will use single constant. So that single constant is Kc. Instead of writing Kf over Kr, which are two constants, we will use a single constant Kc, which is called equilibrium constant. Equilibrium constant is equal to the product of the molar concentration of the product or product of the molar concentration of the reactants. Kf over Kr, the two constants are equal to Kc. Kc is known as equilibrium constant, and the above equation is called as equilibrium expression. That is the expression which is the required expression, and with the help of this expression we can identify that either a reaction is in equilibrium state or it is still in progress or it does not reach the equilibrium state. So by using this expression, we can get more information about a chemical reaction. Kc, the value of Kc is independent on the initial and final concentration of reactants but depends upon temperature. This is very important point for MCQs, that the value of Kc depends on which of the following. They will give you different options. One of the option will be initial and final concentration of reactants, initial and final concentration of product, or temperature or pressure. So the correct option will be temperature. The Kc depends only upon temperature. It is independent on the initial and final concentration of reactant or product or pressure. The only factor on which Kc or equilibrium constant depends is the temperature. Where small c in Kc denotes what? Small c in Kc denotes molar concentration at equilibrium. What is molar concentration? Molar concentration, I told you, molarity. The concentration in molarity is also called molar concentration, and it is equal to moles per decimeter cube. Now, how can we define this expression or equilibrium constant expression in words? So, equilibrium constant is defined as the ratio of the product of concentration of product. Product of concentration of product, C and D are product. And their product means when we multiply these two, product of the concentration of product. Ratio means over or divided by the product of concentration, the product of concentration of reactants, product of concentration of product, or product of concentration of reactants, each raised to the power. Small c, small d, small a, small b are their powers. So in definition, we have also considered the powers. Okay. So each raised to the power. What are these power? These power are their number of moles which appear in the balanced chemical equation. So raised to the power equal to the coefficient in a balanced chemical equation. Coefficient, the number which we write before any reacting substance or any product is called coefficient, or it is also called their number of moles which appear in a balanced chemical equation. Balanced chemical equation, you know that when we write a reaction, the important thing is first we have to balance it. Then it will give us the accurate information. So balanced chemical equation. We can also write it in this form in words. Kc or equilibrium constant is equal to product of concentration of products raised to the power of their coefficients, or product of concentration of reactants raised to the power of coefficients.